Can I ask who you are and what you do?
Well, my name is John Scott, and in early days I spent about 20 years in the very rocket departments of both Bristol Siddeley and then it became Rolls-Royce. Having formed up with my colleagues at Reaction Engines in later life, I'm now the engineering director of the studies going on the different types of space vehicles and so on.
How much of our British space programme do we owe to the German V2s?
Well, to be quite frank about it, we owe a great deal, not just to the V2, but also to the Volta engine company, a Dr. Volta, and he made a small piloted rocket engine to go in the ME-163 fighter, which thankfully was a bit too fast for its own good. Nevertheless, did shoot some bombers down. But the technology was the thing that he'd perfected up in Kiel, I think it was, in Germany. And at the end of the war, two things happened for Dr. Volta. Firstly, he was allowed to work on some of his own projects for a bit, to get them a bit further down the line. And then he came across to England, and his technology was spread partly to the world of submarines, which is what he was working on, peroxide submarines. But an awful lot of it was spread via Westcott and places like that, into the very first English rocket engines that were using peroxide. So that's the peroxide side of the family. On the other side, we didn't directly pick up V2 technology in the same way and try and imitate it. The V2 technology did come into UK, then bounced across to the States. They developed it into the very early thing like a Redstone, for instance, is virtually a rehashed V2. And when requirements arose in this country for proposals to do an early type of ballistic missile, a lot was found to be based on things like Redstone and Atlas and so on, and that technology came back into this country at that stage, having been worked up a little bit from where the V2 left it.
What sort of balance in the early days was there between liquid fuels and solid fuels?
In the very early days, excuse me, solids were merely used for things that you put under the wings of fighters, pointed them at tanks, and they blew tanks up, concrete warheads and things like that. It didn't even have to explode. So virtually nothing in the way of big solids at all. All our early work was on liquid propellants, and there the field was quite wide. They went from quite small things to quite large ones.
So how did the whole liquid fuel technology evolve? What kind of fuels were you using?
In Bristol Siddeley, which is once Armstrong Siddeley, we used all the possible combinations that make sense, and I say that carefully. Obviously, liquid oxygen kerosene is a well-known thing. There were early Armstrong Siddeley engines that used it, but they tend to run very hot, and so they had to use water as well, and that made a tripropellant engine, which, whilst being clever, was complicated. De Havilland's and Napier's went down the line with ministry guidance and funding of hydrogen peroxide and kerosene. This was the logical way to go. I don't even know why Armstrong Siddeley's had been more or less pushed to do this other study. But as soon as they demonstrated that they could do it, they flew it in a piloted aircraft. They worked on another system for what was called the Avro 720, which was an interceptor, proved that got up to whatever the right standard was. But you can't have a fighter aircraft that has to wait to be refueled with liquid oxygen just because the Russians are coming at 60,000 feet. It doesn't make sense. So in the end, they said, we want something that you can put into an aircraft and leave there for a month like you would just kerosene if you have to. And that's where the hydrogen peroxide technology came in. So very quickly, Bristol Siddeley, or Armstrong Siddeley as it was still, changed with, again, the liquid oxygen programs were cancelled, the hydrogen peroxide programs started, and that's what we stayed with ever to the bitter end.
Excuse me. One of the earliest very successful rockets, the one that actually launched our very own Prospero satellite, was Black Arrow. How do you rate the success of Black Arrow, and how would you rate the rocket itself?
A rather splendid piece of equipment, and that's not just because we worked on it. What had happened is we'd had a military rocket program for a thing called Blue Steel, which was a standoff nuclear-tipped airborne sort of bomb thing, flying bomb if you wish. And it produced a small thrust chamber and a large thrust chamber. boost and sustain. Very, very good concept. Such that when this later application came along for Black Arrow, the ministry said, you've got to make this for almost nothing. Typically, don't start redeveloping a new engine, don't do this, don't do that. So you tend to look on the shelf and see what it was that worked well the last time you tried it. And these Stentor engines were proven in every possible way for military service of bad sorts being dropped and bumped and thumped. Do what you like with them, they'll always work. And we made 130 of those, and it was a very successful program. So when they wanted something for Black Arrow, the logical thing to do was to use as many components of a Stentor engine as you could. Unfortunately, it ended up with 8 of the small chambers. Many of us thought we'd have done better with 4 of the large chambers, and the ministry wouldn't have it. It was alleged that it would have fouled the launcher in Woomera or some, what we thought was a not very good excuse. But nevertheless, there were chambers on the shelf ready to be adapted into that programme. And they ran very successfully.
Now, we've been hearing an awful lot today about rocket engines, all kinds of different rocket engines. I'm getting the impression that the Gamma engine is the one that everybody raves about. Why is that?
I think it's basic simplicity and reliability. It was derived as an early Westcott design based very, very largely on Dr. Volta's technology. The point about it is that it has a separate turbopump from the chamber. There's 2 separate things that you merely pipe them together when you've developed them. And that means that they can be developed separately. There were other concepts kicking about, and I'm not going to knock them because they eventually were made to work, but they integrated the turbine with the chamber. And this means that both things have got to have a good day for the thing to work properly. And I've heard a lot of stories from the people who've tried to test them that they didn't always work properly. Whereas we could have separate test beds for separate bits and pieces, and only when they both hit the same magic numbers, if you like, you merely plug the magic numbers together with the pipes and it runs.
So it's not so much rocket science, it's basically rocket engineering.
Very much rocket engineering and hours of development of. Because the thing that often kills them is not the steady running, but the starting and stopping. And things like that. So that's what I call development. We're building up reliability. There's something I used to use to drive some slave experimental pumps. In real life, I think it ran for something like 5 minutes, maybe 10 minutes. I ran the thing for literally hundreds of hours on test beds, and it was just like a motor car. You merely sort of offer it the sort of go signal, and it's running at 40,000 RPM, no trouble. You know, so.
Quick look at other quick questions. Now, what I want to do very much, I want to fast forward now to the future, and I'd like you to tell me about what you're doing with I can never remember the name of the
Skywell.
Oh yeah, I want to go back to Hotel.
Yeah, Hotel.
What the reaction engines?
Yeah.
Yeah.
Well, let's go a jump before that slightly.
Okay, fine.
There was a team, and a very good team, that had launched Black Arrow.
Yeah.
Within days, they'd got to be dispersed. I managed, therefore, to carry on with the research department under the, I think it's still, well, no, it was Rolls-Royce by then, under that brolly, and looked at all sorts of other non-rocket applications of our technology. Now, similarly, Alan Bond, who was a great chap at doing calculations, as well as being just a good engineer anyway, he can do sums much better than I can. And one day he turned up home with this proposal for the better engine, in inverted commas. Like we often talk about the better mousetrap, here was the better engine. Why was it better? Because it was in principle an engine that could run right from ground level all the way up into space and keep going, because it ended up as a rocket engine, and therefore obviously didn't need an atmosphere up there. But the whole thing was designed to be part of a reusable concept. The one thing we realised very simply at the end of the Black Arrow world was that everything we made ended up as a collapsed heat of sort of, looks like Coke cans that had been walked on in the Australian desert, and with a bit of luck, a little bit of it, like only 1 or 2% of it, ends up going around the Earth, and the rest falls down somewhere in the world. This isn't the way to go if you want to put up, say, a whole cluster of communication satellites. Bloke says, I want to put 30 of these up. You can't. It seems immoral, but that's what they're doing. It's throwing away a large number of vehicles for every time you put up a new cluster or renew something. So that isn't the way to go. The fully reusable thing is the way to go. Alan had thought of an engine that would do the whole of the energy spectrum, if you like, and he and Bob Parkinson and myself had done some early sums on what vehicles might look like that would use this engine and how they could fly up into orbit and come down again and land on a runway. And that chugged along for a while, and it started to look promising. And when Alan's engine looked promising enough, he brought this thing home, the brochure. I read it, took a month to go through the calculations because I'm not that bright. And that then meant that I could take it into Rolls-Royce as an engine of the future. And I introduced it to the board as such. At the same time, Bob Parkinson, who was downstairs, made approaches to British Aerospace, which in one way or the other, and said, look, you ought to be looking at this. We've got a variety of vehicles. Let's see what we ought to do. Cut a long story short, because it was a very rough time just forming this group up. But we eventually, with company blessing, and not an awful lot, but just enough to get by, we formed a little, very dedicated group to study this possibility. And we came up with one or two different vehicles. We had the ex-Concorde crew working in on this. I managed to find them, because they understood supersonics and we didn't. So we got them in, and Alan and his engine, and the bit that I had to do, I was good at making things and testing things. So I grabbed a big test bed up at Rolls-Royce, and we started testing bits of air intake systems, things like that. And this worked very well. And then it sort of hit a slow bit. So another chunk of British Aerospace were grafted onto us, and that was the lads at Wharton, who were quite keen to join in. Sadly, they'd only designed fighters and heavy things, and they weren't used to things that would do a different job. But never mind. All became friends in the end. And out of it, this is where we got this HOTOL thing, which we didn't call it HOTOL. We thought this was a disgraceful, horrible name.
I was going to say, why was it called HOTOL?
It's because the British Aerospace let some PR idiot loose once, and they charged him with the duty of coming up with a snap-off-the-tongue name, and it's horizontal takeoff and landing. Well, we said, yeah, that's what we know what this is all about. But what we had done, and I forgot to tell you, is to dedicate the project to Barnes-Wallis, and it was known as the Swallow Project. In fact, because it went into the top, it was known as OS, which was Orbital Swallow. Splendid project this was, and we thought, well, it'll honour the man who used to fly all sorts of funny things down in Cornwall that we only found out about later. He was a very forward-looking chap with hypersonic sort of travel and so on. Anyway, we got lumbered with this wretched name, all of which, of course, was under a secret brolly anyway, so it didn't really matter what you called it. And which was embarrassing because it meant we couldn't even talk to our colleagues about what do you think about when we wanted to share ideas with another engineer. If he wasn't one of this very small team that we created, he wasn't cleared to do so. Anyway, that ran for some years. Wharton got heavier and heavier in their estimates of the thing, and we tried to refine the engine but could never quite chase them up. And in the end, Rolls-Royce said, look, they can't honestly pour any more money on this. And I think about 6 or 8 months later, maybe a year, British Aerospace says, well, look, if we haven't really got a guaranteed engine, we shouldn't be working on this either. So they pulled out. And that left the technology floating about in the minds of only a small number of people. And that's when we took this step of 3 of us forming reaction engines, working from home, starting on what we knew, but not overlapping with anything we'd done before, because some of it had been patented and belonged to other people. So we steered a path that was a new path, knowing of the shortcomings of the existing studies that we'd done, to come up with a new type of vehicle. And this vehicle looked so different. It's a very sensible looking vehicle. The wings are in the right place, the engines are on the wings, everything fits together, and the balance of it is beautiful, because the hydrogen tank is split into 2 and so on. And this was called the Skylon vehicle.
I want to interrupt you at this point and say, did you ever see the original Skylon in London?
No, I never physically saw it myself, but obviously we saw it on things like the Gaumont British films, which was about the best thing you could do in those days. We hadn't got television or anything. But we dedicated it to that because of the shape of our new vehicle just turned out to be a thing that was thin and almost elliptical at the end, or fairly sharp, but it was the body shape was almost the same as that.
How advanced is development on Skylon at the moment?
Well, it's doing very well, because if you look at the problems you've got to solve and you line them all up, some you can solve by sums, Some you can solve by simple tests, and some you can solve by expensive tests. So we did all the sums. Does it still look good? Yes, tick in the box. Move on to the next thing. We need to know more of the aerodynamic characteristics. So 2 sets of wind tunnel work were set in motion, one down at Kingston University, which I went down and ran. That was the low-speed stuff. And some high-speed stuff was run with a friend of ours. He happened to have a continuous running Mach 12 tunnel. So you need small models for that, but we could look at them, and it was an ionising tunnel, so you can tilt the model to all sorts of angles whilst it's running and see the shock waves in real life moving. So you film it like mad. You go home and study all that, and we got ticks in the box for most of that. One very interesting point came out, but that's a detail, something we know we've now got to study a bit more carefully. From that, you can now say, well, what's the next most expensive thing? And that, as became obvious to, even in the HOTOL programme, was the fact that the engine system needs a thing called a pre-cooler. And the whole thing stands or falls on the design of this pre-cooler. It's not just got to sort of cool air from an enormous temperature down to something very low, but it's got to withstand the icing that happens because this is full of really cold refrigerant all the way up the first about 30,000 feet of the sky. And that's the moist bit. There's not much moisture above 30,000 feet. But in the stuff that we're living in here, there's quite a high percentage of water vapour in this room. And you know, your own fridge sort of can often freeze as soon as you take a thing out in a warm room. You'll see it frost. This frosting problem is very severe, and for a long time nobody could solve it. Now, we'd been working on it at Anstey and got some ideas about the basic physics of it, but we hadn't really got all that far down the line. We've refined all that here with a wind tunnel that we've made at Reaction Engines, small wind tunnel, and we're now quite happy about the frosting and control thereof programme. So tick in the box for that. What's the next thing? It's, well, how do you make big heat exchangers? So we set about a programme making big heat exchangers, and we're proceeding very well with that. We've had very little government funding. Just one thing that was useful was a thing called a SMART Award for improvements in technology of manufacture, nothing to do with design and so on. And we've now made 1 or 2 modules, but entirely on private funding. That's what the whole programme runs on. Say apart from this SMART thing, and demonstrated to the rest of the world that we can do this sort of job, but they've not been tested. We've also demonstrated to the rest of the world that there are other uses for this technology. So on the basis of all that lot, we've set up a very special test bed on the site here at Culham, which consists of an old jet engine arranged to draw air through test sections or test modules, if you like. Now, that's all been commissioned, it runs well, it's all computer controlled and highly safe and all the words that they want to know these days. And we're ready to start serious testing at very low inlet temperatures to prove that the engine will still continue to draw air through our modules when they're cooling air. And in parallel with that, we're making actual real modules as well as just a test assembly. So that's where the programme is right at the moment. It has attracted some European funding now, because the Europeans, having been badgered a bit by us, have finally realised that you can use these heat exchangers for things other than a true orbital vehicle that would land, you know, back on a runway and so on. And the question has been posed to us of, can you devise a vehicle, and what is the performance of such a vehicle that would get to the Antipodes in about 4 hours? Obviously, it's got to get a bit of a move on to do this, but we've come out with a number around about Mach 5 as being a good cruise velocity. And so we did some sums on what the vehicle might look like, but more importantly, we're setting to looking at how we adapt our pre-cooled engine technology to a Mach 5 airliner, which isn't the same thing as a thing which starts from zero and spends its whole life accelerating. The airliner accelerates a bit and then hits Mach 5 cruise and goes halfway around the world at that. So that's another study, but we are getting some external funding on that one as well.
Well, that's brilliant news. And look, the question, you probably can't even answer this one. When do you possibly see Skylon actually taking off? Well,
let's answer the question in a slightly different way. If someone came in here with a big bag of money, knowing what we know now, I think there's still the best part of 8 to 10 years to choose a suitable manufacturer, for instance. You've got to trust somebody like MAD. We've had a lot of trouble with manufacturers. One of the things that makes me very sad is that, if I turn the clock back to our rocket years, a lot of technology could be called upon, if you know what I mean. And you knew if you sent out a drawing for something, particularly if it was being made inside our own company, it would come back exactly as you wanted it. That more or less still happens within Rolls-Royce. They obviously have to obey the same rules. But the ability to get things made outside, which is what you'd need for a Skylon aeroplane, because you'd want all the subcontractors making all the bits of the undercarriage and all the hydraulics and goodness knows what, that's almost all gone now. The government's let it all go. And so even when we look around, we almost automatically are driven to looking for European partners. Now, in principle, we're all told to be good boys and be European partners. But in fact, some of the partners, we don't really rate them as terribly suitable, and we're still looking. So that's why it would still take a good 10 years, because I think there'll be a lot of, not mistakes made, but there'll be a lot of trouble achieving the right level of, if you like, dependability, reliability, and so on. Because this airframe's got to be cleared for dozens and dozens of flights. Not like a one-off rocket that goes up and say comes down all shrunk in the desert. This is a regular thing, just top it up with liquid hydrogen and wave it ta-ta again. And that's all, and I really mean that. There's no other thing you have to do to it. So that's the one half of it. The other half, on the engine side, we have in-house programs that show you exactly how to get to the right point in about perhaps 8 years. But then you've got another few years of integration of the engine with the airframe. So sadly, although people like Alan, myself, and our colleague Richard Varville started work on this, I suppose, in probably 1985-ish, I'm guessing a little there, after the end of HOTOL anyway, we're now 20 years down that line, at least from that time. And sadly, we're all 20 years older. And I don't know whether in another 10 years' time some of us will feel like still working on the same project. So that'll be another of the problems. And we are really trying to sort of integrate some younger engineers into our programme.
Well, all I can say is really good luck with the project, because I think it's so visionary. It's wonderful.
Well, I'm glad you think that way. Thank you very much. But the vision, sadly, although we've tried to spread it, it goes up quite happily as long as it's in fairly technical circles. But as usual, when it hits political circles, there are other things on their plates, I suppose, and governments just don't like to commit to that sort of thing. It's got to be a government involvement as well as proper investment. We're not saying it's an all-government thing, because that's not the way to do a programme.
I'd just like to finish with a final question about there've been 4 reports recently about the fact that Britain should be much more involved in the whole space industry, because we risk being behind the Chinese and the Indians and people like that. They've come from the Royal Aeronautical Society, the Royal Astronautical Society, the British Interplanetary Society, and the Select Committee on Science and the Environment from the government. They've all overwhelmingly said that Britain should have a space presence and possibly a human launching facility. What would you say about that?
Well, it's something that's been banned or almost by deliberate intent by the governments for many years. The key answer to all you've just said there is, one word is launcher. Now, years and years back, some bright so-and-so, not quite sure where, but we'll leave that out of this one, decreed, there was one of these select committee report things done, which reported quite well in the favour of what I'm going to suggest. But apparently their message was then twisted as presented in Hansard or whatever, and it now says exactly the opposite. We have copies of this. And the upshot of that was that we said, to get back into this business, you don't want to keep using expendable rockets, buying time on Russian, American, maybe later, as you say, Chinese, anybody's thing, that as long as it goes up and doesn't come down, everybody says that's wonderful, and you buy time on it. The thing to do, if you really want to change the national economics, and I mean there's thousands of jobs we could be talking in this country, aerospace industry, is to make the vehicle that is totally reusable. Now, there's 2 reasons. One is that if you look back over the history of transport, almost everywhere has been opened up either by a good old Leyland lorry that would just keep going forever from A to B, A to B. And the next thing was, when the lorry had taken enough provision to some spot where you wanted to go, you run a good old Leyland bus. And you take the workers to wherever they want to go, and then you can develop a colony or something. This is really, extendable to space-type colonies. You need the vehicle. Because if you could have something that went up to low Earth orbit on a regular 5 times a week, and then you only need a quick shuttle service to the moon, you can have moon colonies as easy as wink, and safe ones, because anybody that gets poorly, and you've got to think about these things, they can catch the next bus back to Earth. Things like that. So the money is made in the vehicles and not in trying to launch these tin pot little satellites on somebody else's rocket. Now, someone years ago, that case having been presented to them, decreed that UK Limited would not make launchers. We'd leave it all to the French. We'd leave it all to the others. We'd buy rides on Ariane, anything you can think of. And we're allowed to make satellites, and some very good ones, the lads at Hawker Siddeley Dynamics was, and all that lot did it, and then the Surrey satellites and all that. It's good business and good luck to them, because it needs to be done. But we could launch those for a fraction of the cost if we actually just built the vehicles first. Now, we've done market surveys of these vehicles, and a fleet of about 18 or 20 of them would in fact, satisfy Earth-type requirements for many years, and they're designed to last for many years as well. But the cost is a bit like Concorde cost. So you've got to start getting nations coming together. Now, there are some nations that you'll never get come together, one of which, I have to sort of say it, is the French, because the Ariane industry, which is as expendable as a toffee paper, it employs thousands of people, and they'll all say, what are we going to do with these people? And the answer is, you can use them to build Skylon. Because once you've used your first batch of whatever it is, they'll get worn out in a few years' time. You can make some more. But at least you have, if you like, you can offer employment to these people. They seem to think that because they're making something expendable, this is bound to go on forever. Well, it isn't. We shouldn't be using strategic materials and chucking them into deserts and oceans all the time, like the big shuttle tank, biggest chunk of titanium you ever throw out of anything. Things like that. This is all wrong. And what you should have is something that, apart from the propellant that was in it and whatever the cargo was, comes down the same as it went up, just like an ordinary airliner. Job done. And what do airliners do? They carry people sometimes and freight other times. And we've got freight versions of a Skylon, we've got people-carrying versions of Skylon that we've studied in conjunction with the whoever it is that used to be the old aviation medicine crew at Farnborough. We've talked to the CAA about legislation, and we've designed a passenger module that will go into the thing, which fits all the modern airliner standards about evacuation and all the things you have to do to sort of make it licensable. So a Skylon, we know, can be a freighter or a personnel carrier, and we're offering it to the world. But at the moment, due to politics, the world doesn't want to sort of chip in on about 3 or 4 governments, chip in with ours. Private investment, we know, is waiting for the first move by governments. They're not asking them to put all the money in by any means, but if there is a first move, they will then see that it's a serious programme. The investors have told us this many times.